So chapter 10 is called Shapes of Molecules, and we finally take all of this information on electrons that we've been learning in our previous chapters and how electrons are shared to form covalent bonds. And when you have lots of atoms that are, connected by covalent bonds, you have molecules, and these molecules have shape. And so we're going to not only be able to think about those shapes, but we're going to learn how to structurally represent them on paper. And so part of that is learning how to draw what we call Lewis structures. And so kind of as a summary of this chapter, 5 skills again that are important, is drawing Lewis structures. And I've called this kind of Lewis structures 101, 201, and 301 because we're going to kind of increase in the complexity in terms of the Lewis structures that we'll draw. And just a comment to point out here, when we say Lewis structures, these are not necessarily as Lewis structures implying information on three-dimensional shape or bond angles or so forth. The more of these that you do, you'll be able to see that. But in and of themselves, Lewis structures simply show connectivity of atoms and show the placement of all electrons. They don't necessarily show three-dimensional shape, and they don't necessarily correctly depict bond angles. So in class, we kind of talked about it as being the difference between Flat Stanley and then Stanley from The Office, who is three-dimensional. And so as we work through our sample problems here, we'll kind of deal with our simple Lewis structures, deal with ones that are a little bit more complicated, have multiple bonds, resonance structures, and so forth, and then get to ones that we call exceptions to kind of our standard rules. And then once we finish that, we'll go into something that's called Vesper Theory, which just stands for valence shell electron pair repulsion. All you really need to think about is electrons want room. Electrons are negatively charged. They want to be as far away from each other as possible. So when we have electrons either on atoms or between atoms as bonds, we need to think about a way so that these electrons are not unnecessarily close to one another, so they're not repelling one another. So all we really need to do is be able to count to 6. I think everybody can count to 6. If you can count to 6, you can figure out the three-dimensional shape of a molecule. Now, again, it's a little bit more complicated than that because we need to count to 6 and then apply that, but pretty straightforward once you understand the theory. And then the last thing that really kind of pulls all of this together is saying, you know what? We learned about polar bonds in our last chapter. Then we learned about shapes of molecules in this chapter. And the two of these actually go hand in hand to determine whether or not a molecule is polar. Because bond polarity in and of itself is not sufficient to predict molecular polarity. We have to think about the shape of that molecule to think about the direction that those polar bonds are pointing. So this will have some more context as we work through some problems in this chapter. So beginning quickly here, we're going to start with sample problem 10.1 on it's kind of a Lewis structure 101 problem, writing Lewis structures for molecules that have one central atom and are pretty straightforward. So with this first problem, I'm going to go through in pretty slow detail how to draw a Lewis structure. And then again, as we build on our future sample problems, I'm going to assume kind of a previous knowledge of and a competency in drawing some of these earlier Lewis structures. So 2 handouts that I provided in class, they both kind of say the same thing, but maybe one you find a little bit more interesting or useful than the other. Here's some kind of directions on how to draw Lewis structures that's based on the schematic that's part of your textbook. And then again, a little bit of thought on formal charge, and we'll apply that in our first sample problem. And then here's another kind of example where we really think about placing our atoms in space, and the glue that holds those atoms together are electrons. And every molecule is only going to have a certain number of glue and a certain number of electrons. So once you glue your atoms together, you need to use up all the glue that you're supposed to use up, and examine your real estate is kind of this concept of formal charges. So whichever of these kind of makes sense to you, use that. They're both going to be kind of looking at the same principles that we'll put into practice with this first problem. Okay, so write a Lewis structure for CCl2F2. Again, one of the compounds responsible for depletion of stratospheric ozone, so one of these ozone depleting compounds. All right, so how do we figure out how much glue we have to hold this molecule together? We have to count valence electrons. So we have to consider the atoms that we have. We have 1 carbon, we've got 2 chlorines, and we've got 2 fluorine atoms. So we consider the number of valence electrons, and again, that's where the periodic table can be a great help for you until this becomes something that's kind of routine in your brain. The group number here on the periodic table basically tells you the number of valence electrons. So again, we're going to be looking for the things that have A's next to them. That tells you the number of valence electrons that these atoms have. So again, carbon is going to have 4 valence electrons. And because we only have 1 carbon, that's only 4 electrons of glue that we're going to be contributing here. Chlorines and any halogens are going to have 7 electrons. So fluorine will also have 7 electrons. There's 2 chlorines, so that's a total of 14 electrons, 2 fluorines, and that's, again, 14 electrons. 2 chlorines, 2 fluorines, 14 electrons for each of those 2, so total of 28 electrons plus 4. We're going to have 32 electrons that need to glue these atoms together. First step, again, figuring out the number of electrons that you have. So again, we need to think about valence electrons. We want to space our atoms out to be glued together. And how you space them out is whoever has the lowest group number. So these, again, are our group numbers. So whoever has the lowest number, we can also think about this, whoever the least electronegative is going to become a central atom. We're going to put them in the middle. So in this case, it's going to be carbon. So we're going to put carbon in the middle, and we're going to place our fluorines and our chlorines around it. And remember, because Lewis structures simply indicate connectivity, where we place these atoms relative to one another, in terms of I could put chlorine up here and a chlorine here, that doesn't matter at this point. All right, so kind of following along, whatever you want to follow along with, we spaced our pieces, we spaced our atoms. Again, arranging atoms in our space. We determined how much glue we have, that's summing up the valence electrons. Now we're going to glue our atoms together, and we glue things together first by connecting only with single bonds. So every time I draw a line, that represents a single bond with 2 electrons that's gluing those atoms together. What I'm going to do now is account for the fact that I've used up 8 electrons worth of glue, right? Learn to count by 2 when we do these. It's going to make counting so much easier. Every bond represents 2 electrons. So 2, 4, 6, 8 electrons have been used up with my single bonds. That means I've got 24 electrons left over that need to become part of my molecule. So again, looking at our kind of directions here, we glued our atoms. Now we need to use up our glue. And the directions here say add the remaining electrons to any atoms that do not have a complete octet of electrons. Again, with the exception of hydrogen, that's the duet rule. Make sure don't use more glue than you have. And some rules that were more specific with your textbook here. It says distribute the remaining electrons in pairs so that each atom has a complete octet, and again, a duet for hydrogen. Work first with the surrounding or more electronegative atoms. Place any remaining on the central atom. Again, Lewis structures do not indicate shapes, so there's several correct ways to draw bonds between atoms. Note that the connectivity will remain the same with them all. So again, just reviewing some of those rules we already talked about. 24 electrons to go around. I'm going to start with my peripheral atoms first, and I'm going to count by 2s. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. At that point, I've used up all my glue, so there's no electrons left to go on my central atom. As we'll learn in a little bit, that's a good thing. Does everybody see here that carbon has 8 electrons around it? 2, 4, 6, 8. One of the things that we'll talk about in a minute is that it doesn't own all 8 of those electrons. It's sharing those electrons with fluorine. So we're going to think about this in terms of what we referred to in our opening discussion as formal charge. Okay, so we can define formal charge, which I'm going to abbreviate as FC. So formal charge is basically the difference between the number of electrons an atom wants And that's the same thing as its valence or group number. Okay, it's the difference between the number of electrons an atom wants and the number of electrons an atom has. Okay, and let's use a different word here. Let's not say has, let's say owns. Okay, an atom is going to own 1 electron of every 2 electrons in a bond, and it's going to own 2 electrons of every lone pair. Okay, so let's run through this as an example with these atoms here. Let's start with carbon. Carbon wants 4 electrons around it. It has 8 electrons because it's sharing, but it wants only 4 of those 8. How many does carbon atom own? Carbon owns half of that 2, half of that 2, half of that 2. So again, when we count, and we count with bonds, I'm going to count by ones. 1, 2, 3, 4. This carbon atom owns 4 electrons, and it wants 4 electrons based on its valence. So the formal charge on this carbon is 0. Usually formal charges that are 0 are not written, but just because we're learning about them, I'm going to write them on these atoms. Chlorines, or any halogen like fluorine for that matter. I'm going to count the number of atoms this chlorine atom owns. It owns all of our lone pairs, so 2, 4, 6, and half of these 2, 2, 4, 6, 7. This chlorine atom has 8 electrons around it. It owns 7 of those electrons, and that's exactly what it wants to own because its group number is 7 and it had 7 valence electrons. So in this case, the formal charges on the chlorines are 0, and the same thing with the fluorine atoms. Again, when you don't have a formal charge, that is the formal charge is 0, typically you don't write anything down. But just because we're learning about what formal charge is, I wanted to draw it here. As we'll learn about in a little bit, the best Lewis structures are ones that have the fewest formal charges or formal charges distributed according to electronegativities. That will make a lot more sense when we do a few problems in the next few sample problems.